We're tackling binary search, which we want to try and solve with minimum complexities of O log n time and O1 space. We're given an array of integers, nums, sorted in ascending order. As well as this, we're given a target. We need to write a function to search for target within nums. If that exists, then we're going to return its index. Otherwise, we're returning -1. It's absolutely essential that you write an algorithm with O log n runtime complexity. There are 4 possible methods, and you really have to think hard about this. A. Linear search. B. Count sort. C. Kruskal's algorithm. Or D. Binary search. I'll pause for a few seconds, and I hope you didn't need too much thinking time. The answer is D. Binary search. Obviously, the brute force approach will involve a linear scan, and it's quite well established, and I think it's basic data structures and algorithms that the binary search is better than the linear search for a sorted array. So, rather than read this out to you, I'll just show you very quickly the code that we're going to use for a binary search. So the binary search algorithm efficiently searches for the target within our sorted array. The key idea is to repeatedly divide the search space in half until we find the target or determine that it doesn't exist within our array. Obviously, since we're not guaranteed that we'll find it, we'll initialize ants to -1. But let's do a line by line, just for completeness. So we start with the variables start and end, initialized to the first index and final index of the nums vector, respectively. As mentioned, we initialize the variable ants to -1, which will store the index of the target if found. We then enter a while loop that will continue for as long as start is less than or equal to end. Inside the loop, we calculate the middle index, mid, and we use the formula start plus end minus start divided by 2. This ensures we always select the middle element between start and end. After that, we compare the value at nums mid with our target. If nums mid is less than the target, it means the target must be in the right half of our search space. In that case, we update start to mid plus 1 to search for it in the right half. Conversely, if nums mid is greater than target, then it means the target is in the left half of our search space, or the left-hand side of our array or subarray. We update end to mid minus 1, meaning that we'll be searching in the left half. It's probably easier to visualize something like this if you go through it looking at one of these arrays. So each time, for example with the target 9, we'd first look at the middle index. We'd see something like, let's say 3, go, oh, well, the target is greater than 3. We need to check from start here and end here, look in the middle, and we see, oh, we've reached our target. In any case, the final part of the while loop was that condition where nums mid equals target. If that's the case, then we'll assign that middle index to our answer and break out of the loop. So, whether we've broken out of the loop by finding the target or not, after the loop we're going to return ants. This will either represent the index of the target if we found it, or -1 if the target doesn't exist in the array. So, that's it. I will recommend this course before I finish. There are a litany of binary search problems that are covered in the Algorithms Part 1 course, as well as slightly better instruction than I can provide. Anyway, I recommend using our application in conjunction with the course, especially if you're doing the algorithms course. It's quite challenging towards the end, I promise. For this problem, of course, I won't waste your time any further. The Y button will give an explanation as to why we use the binary search, although in this case we've kept it to a minimum. If you really need the code here, you can check it out in C++, Python, and Java as well. I can assure you that these ones are all correct and have been tested on LeetCode as well. So that's everything. We're going to be tackling a more challenging problem next, and it's find first and last position of element in sorted array.